Hey everyone, and welcome back to the channel. Today we're diving deep into the fiery heart of our planet to uncover a fascinating secret about volcanic eruptions. You know, we often picture volcanoes erupting suddenly, a dramatic explosion out of nowhere. But what if I told you that some of the most powerful eruptions are actually the culmination of a slow-burning process, sometimes taking weeks, even months, after the initial trigger? That's right. We're talking about the incredible, often delayed link between magma mixing and explosive volcanic events. It sounds counterintuitive, doesn't it? Magma mixing. You'd think that's the immediate signal, right? But recent research using incredibly clever techniques is showing us that the journey from two distinct magmas meeting to a full-blown eruption is far more complex than we ever imagined. It's not just a simple stir and blast, it's a chemical dance, a pressure cooker scenario that takes time to build up to its grand, explosive finale. So let's break it down. Deep beneath a volcano, there isn't just one big pool of molten rock. Often there are multiple magma chambers, each holding different types of magma. Think of it like layered cakes, or even different types of liquids in a complex cocktail, each with its own temperature, viscosity, and chemical composition. When new magma, perhaps hotter and more buoyant, rises from even deeper within the Earth, it can intrude into an existing, cooler magma chamber. This is where the magic, or perhaps the volatile science, begins. When these different magmas meet, they don't just instantly blend. It's a process. Imagine pouring a thick cold syrup into hot water. They don't instantly become one homogeneous liquid, do they? There's a period of stirring, mixing, and reaction. In the case of magma, this mixing can be incredibly significant. The introduction of hotter, gas-rich magma into a cooler, often more viscous magma, can initiate a chain reaction. The cooler magma might already be partially crystallized, making it denser and less prone to flow. But the new hot intrusion can trigger a whole host of changes. One of the most crucial elements here is gas. All magma contains dissolved gases, like water vapor, carbon dioxide, and sulfur dioxide, held under immense pressure. When hot magma mixes with cooler magma, it can cause the dissolved gases in the cooler magma to exsolve or separate out, forming bubbles. Think of opening a soda bottle. The drop in pressure releases the dissolved CO2 as bubbles. In a magma chamber, this gas exsolution drastically changes the magma's properties. It becomes more buoyant, less dense, and crucially, more explosive. But why the delay? Why weeks or months? This is where the physics and chemistry get really interesting. It's not just about mixing. It's about the time it takes for those new gas bubbles to grow and coalesce. It takes time for the magma to become fully saturated with these new bubbles, time for the viscosity to change significantly, and time for the overall pressure within the chamber to build to a critical point. Scientists study this by looking at the tiny crystals within erupted volcanic rocks. These crystals are like miniature time capsules. They record the conditions they grew under, including temperature, pressure, and the composition of the magma around them. When magma mixes, these crystals can show distinct zoning, layers that reflect changes in the magma's chemistry over time. By analyzing the growth rates of these crystals, scientists can actually estimate how long it took from the moment of mixing to the moment of eruption. And what they're finding is often a surprisingly long period, not days but often weeks or even many months. For example, studies of certain eruptions have shown evidence of distinct magma mixing events that occurred several weeks before the actual explosion. The implications of this are huge for how we monitor and predict volcanic activity. If we can detect these mixing events, we might have a much longer window of opportunity to understand that an eruption is building, giving communities more time to prepare or evacuate. This delayed response highlights the incredible complexity of volcanic systems. It's not a simple switch that gets flipped. It's a dynamic, evolving process where the interplay of temperature, pressure, gas content, and chemical reactions all contribute to the ultimate outcome. Understanding these delays is crucial for improving our hazard assessments and ultimately, for saving lives. So the next time you hear about a volcanic eruption, remember that it might not be a sudden, spontaneous event. It could be the grand finale of a long, unseen drama unfolding deep within the Earth. A dramatic chemical reaction initiated weeks or months before the first puff of ash or flow of lava. It just goes to show how much more there is to learn about our incredible planet. Thank you so much for joining me on this deep dive into volcanic science. If you found this as fascinating as I did, please give this video a thumbs up, subscribe to the channel for more mind-blowing science content, and hit that notification bell so you don't miss our next adventure. We love hearing your thoughts, so leave a comment below. Until next time, stay curious. Next time, stay